We've talked about comparing practice performance for water quality improvement and about comparing practices based on stackability. In this lesson, we'll continue to compare practices and we'll move on to comparing practices based on their implementation barriers and their ease of implementation. You saw this table in the last lesson when we talked about stackability, and now we're going to jump to the middle column, which is labeled production system change. In this qualitative assessment, using ranking from 1 to 5, a 5 indicates a relatively large change would be required of a producer to implement a given practice. If we go back to those land use change practices as examples, while they have very high water quality improvement efficiencies for both nitrogen and phosphorus, they also have some real barriers for their adoption. These land use change practices require a pretty big change in status quo in terms of doing things differently on a farm. You really see that illustrated in the scores when you compare these practices to, for example, tweaking how nitrogen fertilizer is managed or performing soil testing for soil test phosphorus, where we would consider the bar to be a little lower in terms of changes in a production system. Another pretty significant barrier to practice adoption is time. Not just required change in status quo, but the time some of these practices take to do. Some practices require landowners to do certain management activities in windows that are already pretty busy with other field activities. For example, spring application of nitrogen or terminating your cover crop in the spring can be real concerns in terms of your production timeline. It's also worth mentioning that the risk, or even the perceived risk, of not getting important springtime operations done can be a real barrier to doing some of these conservation practices. There's been some wonderful work about barriers to the adoption of conservation practices, and I'll just highlight some recent results from Dr. Prokopi's group at Purdue University, where they found that variables positively associated with adoption include the farmer self-identifying primarily as stewardship motivated, the farmer had previously adopted other conservation practices, they were aware of conservation practices and programs, maybe they had land they had identified as vulnerable. These farmers who had adopted conservation practices tended to have greater farm sizes and higher levels of income and formal education. And they also expected a positive yield impact, which is an interesting final point and definitely a clear motivator. Another way conservation practices can be compared is in terms of additional ecosystem services that those practices provide. In this course, we're really most interested in drainage water quality, but of course some of these practices provide additional benefit to the environment and to society. I'm showing a table from a study I did during my PhD comparing some ecosystem service potential of some conservation drainage practices. Most of the additional services provided by these practices are the regulating type of ecosystem service, like shown in the middle row. These services include regulating air or erosion, or providing pollination or water purification. Not surprisingly, many of the practices that provide the most ecosystem services are practices that have vegetation associated with them, like wetlands or cover crops, compared to practices like improved nitrogen fertilizer management, bioreactors, or controlled drainage. You'll remember this table from the earlier lesson. See how they've also provided information on soil health and wildlife habitat for this range of practices. Obviously, the edge of field practices don't do much for infield soil health, which this table nicely illustrates. We also previously talked about the Nature Conservancy's Edge of Field Roadmap, and they provided a summary table for these edge of field practices that lists what they call co-benefits: wildlife, pollinators, water and carbon storage, and crop yield. Not surprisingly, wetlands, prairie strips, and vegetative buffers rank very highly here in co-benefits. But keep in mind, for our drainage context, it's really only wetlands out of those three that provide actual drainage treatment. I also want to highlight something that we touched on in the last lesson: data uncertainty for these practices. I like how this table reflects the robustness of the body of literature for each practice. We know a lot about wetlands because scientists have been studying those for a long time, but you can see we have a lot more to learn about many of these edge of field practices. The last resource I'll mention here is that the USDA NRCS has also assessed each of their conservation practices in terms of physical effects. Or in other words, they have assessed each of their practices in terms of the overall environmental effect that given practice has. This matrix of conservation practice physical effects is publicly available as a spreadsheet where every single NRCS practice from an access road all the way down to windbreaks, is rated from a +5 to a -5 for any possible type of physical effect. And these physical effects include possibly causing erosion, subsidence, compaction, ponding, seeps, drifted snow, water quality and quantity impacts, temperature impacts, pest pressure, objectionable odors, wildfire hazard, pretty much any possible physical effect. Suffice to say, the NRCS has taken effort to qualitatively rank all of their practices for each of those physical effects categories. One last important aspect to mention is that these practices that we're talking about vary in their ability to be tracked and reported. Remember, for our state strategy process, it's not enough to just develop a state strategy or even start to put conservation practices across the landscape. We also need to tell the story of what we're doing back to the Hypoxia Task Force and essentially back to US Congress. For example, like with the biennial reports that the state of Illinois publishes every 2 years. I'll remind you that it takes time, lag time, for the positive impact of a conservation practice to be felt in the water body of interest. This means that there is a lag time between when we actually do a practice, like when we build a bioreactor, and when the reduction in the size of the hypoxic zone in the Gulf of Mexico will be consistently measured. Until we can actually document the desired improvement in downstream water quality, we need to track and report what conservation practices we're doing to help better illustrate the progress that we're making. There are certain practices that are really hard to track. The way we manage our nitrogen fertilizer is a prime example because these are often privately made decisions or decisions made with just a co-op or an agronomist. On the other hand, there are practices that are relatively easy to track, like wetlands or bioreactors, because you can physically see that it exists and you know that that practice will be there operating feasibly for its entire functional life. Land use changes are also easy to verify via satellite imagery for tracking purposes. See you next time.